on helping the largest energy providing county in the state to come to grips and really build a strong air quality program. I do have a lot of information to get through, and I do want to take your questions. So if you could put those into the chat, I will try to address those at the end. So since 2019, the Colorado legislature has been very busy with sweeping environmental legislation, starting with Senate Bill 181, which enacted extensive additional rulemaking to place more controls and reporting on the oil and gas industry. There'll be more on that on the next slide. Senate Bills 96 and 1261, which set the greenhouse gas roadmap and reporting requirements in motion. We have Senate Bill 204, which establishes an air quality enterprise fund for research analysis, which is now off the ground and running and into rulemaking. House Bills 1265 and 1189 that are further regulating air toxics. There's pending regulation in front of committee right now to put even stronger air toxic regulations in with health-based standards. And then most recently, the Senate Bill 260, which I think has now morphed, requiring sustainability initiatives in the transportation system. And we see CDOT and CDPHE struggling to enact regulations relative to Senate Bill 260. So Senate Bill 181, which kicked all this off, called for a series of new rules on all aspects of oil and gas operations, further reducing emissions on what's already a very tightly regulated industry when compared to other operating areas in the United States. So as you see here, the rules address additional requirements, including leak detection and repair, pneumatics, storage tanks, and engines. 181 also entertained several alternate proposals for ozone non-attainment area boundary, offsets, and mobile source emissions. As you can see through this list, CDPHE left no stone unturned when it came to regulating the oil and gas industry in Colorado. Further, the legislative requirements spawn rules for greenhouse gases, including reporting and the enactment of reduction targets. This is known as the GGH Roadmap across all sectors. The reductions call for a 26% reduction from baseline by 2025 and a 90% reduction in GHG by 2050. I would highlight that the rules don't offer a how-to. They only set the target, and there's much debate about the baseline inventory methods, the accounting methods to show the reductions. And we'll talk a little bit about that later. And finally, the 2021 rulemaking and the planned 2022 rulemakings for transportation, oil and gas, building efficiencies, and regulations on energy-intensive manufacturing. This could be a presentation in of itself, but we're going to touch on some key issues surrounding greenhouse gas and energy a little bit later in the presentation. So finally, Colorado changed the mission of the Colorado Oil and Gas Conservation Commission from a prevent and mitigate to a protect and minimize. This was referred to as the mission change rulemaking. And it was so moving to this protect and minimize adverse environmental impacts. This was a fundamental shift in what the Oil and Gas Conservation Commission needs to do. It's key to note that in the mission change, the language requiring the commission to consider cost effectiveness and technical feasibility was struck from that language. But the rulemaking that came out of this mission change established a 2,000-foot setback from residential buildings, schools, and child care centers. I would note that the setback was not grounded in any health risk assessment, but was set based upon a distance that public commenters and the commission deemed appropriate. We'll talk a little bit more about air quality health risk assessments at the end of the presentation. Also, this mission change established a requirement for cumulative impact assessments akin to those under the National Environmental Policy Act. However, unlike NEPA, this rulemaking does not have a framework, and nor does the commission have the experience or expertise yet in environmental impact assessments to actually execute this mission change. So this is pretty basic, particularly for this audience, but I think it's really key to frame this up. When we're discussing environmental air quality, it's critical to understand that there are three distinct classifications of air pollution. And oftentimes we see the, public commenters and community scientists conflate the issues. Each of these have distinctly different different impacts, scientific drivers, and therefore policy drivers. So first, there's criteria air pollutants, referred to as such because they have established primary and secondary ambient air quality standards or criteria that must be met. And the state agency, the CDPHE, has a legal obligation to ensure that its air quality meets these standards. As such, these 6 pollutants are the primary drivers for air permitting and statutory control requirements in the state. Today, we're going to focus on one of those, which is a really important one, ozone. Greenhouse gases consist of 4 primary pollutants, carbon dioxide and methane being the dominant ones that retain radiant energy and result in anthropogenic climate change. These are regulated through a GHG reporting programs, and importantly, these are mesoscale, not microscale pollutants, and this will become important when we talk about life cycle. And then finally, there are hazardous air pollutants or air toxics. And EPA has established 187 of these that are federally regulated under the NESHAP, and the state has other toxics of concern such as hydrogen sulfide. These pollutants are harmful to humans at certain doses and durations, and we'll talk about air toxics again at the close of the presentation. So let's start with ozone pollution and the path to attainment. I think the first thing to remember is that ozone is not emitted. It is formed in the troposphere in a very complex reaction. Certain volatile organics, not methane or ethane, but VOCs that are propane and higher, form free radicals which react with oxygen in the presence of UV radiation to form ozone. And then nitrogen oxides work both as a catalyst and a scavenger to increase the rate of reaction, but are also consuming reactants. The takeaway from this is that this is a very complex reaction that depends upon meteorology, topography, the relative concentrations, and the specific VOCs emitted. Certain VOCs like aldehydes are highly reactive, whereas certain VOCs such as propane are not very reactive. So not all VOCs are created equally. So we can monitor the ozone concentrations because it's not emitted. How do we know where it comes from and what sources contribute the most? And as you would suspect, it requires some pretty sophisticated models. Depicted here are the ozone monitors in the Denver Metro North Front Range and the maximum concentrations that they are monitoring. And the isoplet that you see shows a probabilistic distribution of the origin of emissions that form ozone that are transported to that monitor in the previous 24 hours. The model, high split, is a back trajectory points, calculates back trajectory points for each hour in the 8-hour period for the 4 highest daily maximum 8-hour concentrations each year. And this is for 2017 to 2019. Those are presented here. The analysis shows that the sources in the areas in orange and yellow are most likely contributing to high ozone. While the areas in the cooler shades, the greens, the purples, are most likely do not. Interestingly, what we see is this finger of green. If you look here, if you can see my arrow, from the Fort Collins West monitor that follows the Cache-Laputer that shows elevated contribution. This depicts a channel flow of emissions upslope to the monitor. We note on this figure areas in the north and east Weld County that show low frequency of contribution. What this did is it identified a monitoring gap in this region here in the southeast area of Weld County, as well as to the north and to the east, where we didn't have enough information. So what we did next is to install monitors. So Weld County constructed and now operates 3 new monitoring stations, which began operation in the first quarter of 2021 to address the monitoring gaps. You see Missile Site Park here near Greeley is to observe the transport in the Cache-Laputer River drainage. The Hereford site at the very northern boundary of Weld County and the Orchard site right on the boundary between Morgan County and Weld County are there to monitor boundary conditions. And each site is equipped with ozone monitors and meteorological towers. The MSP, the Missile Site Park, and the Orchard sites also monitor nitrogen species for both ozone and regional haze modeling. In addition, the Regional Air Quality Control Council conducts regional photochemical modeling to assess the sources of air pollution that contribute the most to ozone formation at the violating monitors. This information is used to inform the state's plan to regulate emissions to bring the area into attainment. Shown here is the distribution of sources within the non-attainment area contributing to the highest measured ozone days. What we see is that the major contributors change as we go from north to south. At the Fort Collins West monitor, we see oil and gas sources contributing 34% of the ozone and decreasing to only 11% as you travel south to the Chatfield monitor. The Fort Collins West shows the impact of the potential for emissions transport. Conversely, motor vehicle, lawn, and construction contribute more as you travel south. So what does this mean? It means that the profile of emissions and the necessary controls vary from north to south. It also shows that where the monitors are highest, the impacts are driven more by residential and commuter emissions than by stationary sources. Additionally, the RAC evaluates the contribution of violating monitors based upon geographic distribution of the sources. This map depicts the modeling domain, and the sources are aggregated into the east, west, non-attainment area, and the northern Larimer and Weld counties, an area recently identified for inclusion in the non-attainment area. The gray indicates boundary conditions or ozone being transported into Colorado. The pie charts on the right then show the distribution of contribution of those regions to the modeled ozone concentration. And this thin blue sliver that you see in each of the monitors at 12 o'clock position shows the contributions from the northern Larimer and Weld County, less than 1%. It's interesting, though, that there seems to be very vocal public call to include this region, and in fact, EPA has just moved to include this region in the non-attainment area for no other reason than it couldn't hurt. So I now want to discuss recent trends of emissions in the DJ Basin using more modern technology. The Atmospheric Infrared Sounder, or the AIR satellite, was launched in 2002, and it collects measurements of various pollutants globally. It orbits pole to pole and passes over the DJ Basin at 1:30 a.m. and 1:30 p.m. daily. Ramball analyzed the grid cell over the Denver Metro and the portion of the Northern Front Range, what we call the Denver DJ Basin Cell, or DDJB. And then based on this AIRS data, ambient methane concentrations adjusted for background using the Mauna Loa Observatory have decreased 52% in the Denver-Julesburg Basin since its peak in 2013. Yet according to COGCC records, oil production has doubled and gas production was up 20% across the same period. Now, I would also note that ground-based monitoring of both methane and ethane corroborate these trends, particularly at the Platteville monitor. This demonstrates the efficacy of the regulatory controls in Colorado since 2011, but it also suggests that the bottom-up oil and gas inventories do not adequately account for the recent regulatory changes or operational controls. Simply put, it's not the same air that we had in 2011. So what are the implications to community science and public policy? For starters, ozone is complex, and you cannot point to a single industry or source as the cause. There are multiple factors that vary regionally across the U.S. and within the region, like the North Front Range, as well as seasonally, summer versus winter. The models show significant influence on ozone from transport into and within the region. And as I said previously, the ozone drivers are not the same that they were in 2011, so we need to update the narrative. Finally, modeling is a key decision tool to test the impact of regulations and policies. More and better monitoring, as embarked upon by Weld County, improves the predicted values of these models. But there's still additional modeling or monitoring that can be done in other contributing regions that could improve the efficacy of these models. So I'd like to switch now to greenhouse gases and talk a little bit about those and how they're regulated. So the most important thing to remember about greenhouse gas regulation is that it is a mesoscale issue and that you must consider emissions across the entire supply chain. Emissions are broken into three categories or scopes. Scope 1, which includes direct emissions from sources that are owned or controlled by the company, Examples are stationary combustion sources such as generators, boilers, on-road mobile combustion, off-road mobile combustion, and the fugitive emissions. Scope 2 is the indirect emissions from purchased energy consumed by the company. And these Scope 2 emissions physically occur at the facility where the electricity is generated. So this is, simply put, purchased electricity, heat, or steam. And then finally, the Scope 3 emissions. These are the indirect emissions from upstream or downstream of the operations. This would include things such as employee commutes, waste disposal, business travel, and other emissions in the supply chain. But these are also the emissions from, these are the emissions from the end use of the product. And this becomes important when we talk about life cycle. So on the left here, you see the distribution of emissions across the supply chain from an aggregate of midstream operations. You will note that the emissions are dominated by Scope 3 downstream emissions. This means that the largest contribution of oil and gas to GHG emissions is not in its production, but it's in use. This is predominantly driven by using hydrocarbons in combustion as opposed to using hydrocarbons for feedstocks, where the carbon remains sequestered in the product. Note that the intensity of the oil and gas production does not contribute a large portion of the total life cycle emissions for oil and gas. I will note that given the magnitude of U.S. production, it is important to take note of which producing basins have lower emissions intensity. On the right, you'll see that the Denver Basin here is relatively low intensity and high production, while the Piceance Basin here is relatively high intensity and low production, meaning that production in the Denver-Julesburg Basin contributes less to life cycle emissions than production in the Piceance Basin. So there's been a lot of talk about electrification as the solution to greenhouse gas emission, and that depends. It depends on the efficacy of the electrification, or the efficacy of the electrification is regional due to the carbon intensity of the power production fleet and the purpose for which the electricity is used. For example, here we see the carbon intensity of the various power producing regions in the US, with the Rocky Mountain coming in at the 5th highest at 1,243 pounds per megawatt hour. I did some math, and natural gas reciprocating engines have a carbon intensity somewhere between 1,000 pounds per megawatt hour for large and efficient units, upwards of 1,600 pounds per megawatt hour or greater for smaller, older, and less efficient units. So electrification is not necessarily better as a rule, notwithstanding that it doesn't consider the indirect emissions, the capital infrastructure required, or the safety and reliability requirements. Simply put, it doesn't necessarily, electrification, unless you can get below the 1,243 pound per megawatt hour, doesn't necessarily solve the problem. Additionally, let's look at vehicles. There's been a lot of talk about the electrification of fleet vehicles. It's a more promising story. According to the manufacturers, electric vehicles range anywhere from 24 to 30 kilowatt hours per 100 miles traveled. On our grid, that equates to about 0.3 to 0.4 pound per VMT. That's a little less than half of the average fossil fuel vehicle. So there's some promise in fleet vehicle electrification, presuming we can resolve issues of availability, infrastructure, reliability, and range to meet consumer needs. And in fact, with the E-Trip program that was scrapped last year, this was the primary consideration that sent CDOT and the Energy Office back to reevaluate the employee trip reduction program and some of the CDOT rules that are coming forth for the fleet, medium, and heavy duty vehicles. So to recap, greenhouse gas and climate change are global, not local issues. I think that's an important distinction. Local concentrations of GHG do not necessarily correlate to global temperature impacts. GHGs don't recognize political boundaries, so policies have to consider leakage or the migration of GHG emitting sources to less regulated environments. And that we don't make policy that incentivizes production and consumption of energy where it is less efficient or beyond our control to regulate. If you remember nothing else about GHG, consider the life cycle analysis of your project or your policy. In oil and gas, direct emissions are a fraction of the carbon intensity. Instead, we will move the needle not by regulating its production, but by curbing its combustion. The accounting and the inventories need to be rigorous, and consistent. There has to be transparency and verification to preclude double counting and ensure that we have real reduction. And then finally, electrification is not a panacea. It's a tool in the toolkit, but it's not the only one. And unfortunately for some folks, when all you have is a hammer, everything looks like a nail. So I want to move to air toxics and discuss a little of our work there. So there's been a lot of attention given to air toxics and the impacts to communities, and there's been a lot of citizen science and quite frankly, some misinformation regarding air toxics. I want to review some lessons learned from a case study that in Greeley, the Belo Romero Academy, where Ramball's air toxicologists did an independent review of data collected by CDPHE, and there were some important points that came out of it. So the CDPHE stationed a mobile air monitoring lab called the CAMEL to detect speciated volatile organic compounds in the ambient air on a school's campus located 1,400 feet from a production facility. There were 3 monitoring periods at the school between May and November of 2019, amounting to almost 1,800 hourly samples. And in those 1,800 hourly samples, the state observed a single occurrence of a 45-minute sample on November 5th, 2019, that had a benzene concentration of 14.7 ppb, and that raised concerns and prompted follow-up monitoring in December. So our toxicology team obtained the raw data and we independently evaluated it. What you see here are the benzene concentrations at parts per billion, note parts per billion with a B, measured in ambient air during the multiple phases, beginning with fracking all the way to flowback. The lines on the graph are the acute exposure guidelines, meaning these are the concentrations below which no observable effects would occur even in the most sensitive populations. And I think that's key to note. That is, even in the most sensitive populations. We'll talk more about how these guideline values are established in the following slides. So the Agency for Toxic Substances and Disease Registry, or the ATSDR, which is a part of the CDC, establishes a minimal risk level for exposure over 1 to 14 days of 9 ppb. And you hear that 9 ppb number thrown out a lot. What I want to be clear is that is an exposure standard not on an hourly basis, but up to 14-day average exposure. The other standard thrown around is the California OEHA standard, which is acute, 8-hour exposure of 1.2 ppb. So this one sample was 14.72 ppb for less than an hour. It was surrounded by 23 other samples in the same day, all below the 1.2 ppb standard. And this suggests that while something may have occurred on that date, it was a brief event that did not reoccur, and the exposure duration was less than both the 1-day or the 8-hour exposure guideline. So the previous graph assumed that the exposure was continuous, but it is not, as the students and the staff are not present 24 hours a day, 7 days a week. Further, the instantaneous exposure is not a good metric for a comparison to the lowest threshold, which is the California 1.2 ppb standard. So we calculated the average over 8 hours, which is appropriate to the comparison to the 1.2 standard, and gave us a more realistic comparison. The green bars here represent the 8-hour core school day period, 8 a.m. to 4 p.m., and the blue bars represent a 12-hour extended school day period, which would be a 6 a.m. to 6 p.m., and this would account for before school and after school activities. All days, Monday through Sunday, are included. The green hatch bars reflect days when less than 6 samples were available for averaging for core averages, and the blue hatch bars reflect days when less than 9 samples were available. So these would be days that would eventually be excluded. The solid lines represent the 8-hour REL, the 0.9 ppb, or the ATSDR MRL of 9 ppb. One of the core school day exceedances was for a day when the standard data analysis would exclude the average because it contained less than 75% samples. And the other 2 exceedances were very close to that OEHA benchmark. Although taking the averages during extended school day resulted in 12 days with exceedances, all of these 12-hour averages only exceeded the REL and not any other risk assessment values. These averages were all below 1.9 ppb, and they do not reflect really high values. So I know this is intense, so bear with me here because I'm going to get a little nerdy. The question always comes up, how much is safe? Or worse, the comment that the only safe dose is no dose. The key to remember is that these guideline values are rooted in actual health studies based on observable effects that occur relative to measured exposures, usually in animals. Toxicologists look at the universe of these tests shown here, and they pick the most sensitive species at the most sensitive endpoint. And benzene has many studies. Every one of these represents a benzene study. And then to be conservative, you decrease the value to account for each uncertainty. So if you're dealing with interspecies, if you're dealing with sensitive receptors, an additional order of magnitude is applied to arrive at a screening value. And this is usually orders of magnitude lower than where any adverse effects were actually observed in the studies. So you compare the MRL to the background benzene. Here we see the concentrations where effects were observed. Note that this scale is logarithmic. Actually, let me back up. Then based on the most sensitive study, most sensitive species, most sensitive endpoint. And because of all the conservatism to accommodate these uncertainties, i.e. species variability, sensitivity population, the MRL is over 1,000-fold lower than the dose that was in this most sensitive mouse study. The California 8-hour LRL was developed based on a study in worker populations where individuals were exposed to high concentrations of benzene. For health protective purposes, that same study was used for long-term exposures and then used to derive that 8-hour standard. In the study, the workers were employed an average of 6 years, and the concentrations that they were exposed to exceeding 10 ppm or 10,000 ppb. The lowest benzene concentration where any health impacts were observed occurred at exposures of 570 ppb. Now, what this means is that exposure to a level above the minimal risk level does not mean that adverse health effects will occur. Now let's put the exposures into context with typical background concentrations. This is a metric that's much easier for laymen to understand. The max daily average concentration at the Bella Romero was 2.1 ppb. Ambient air in Denver measured in 2016 and indoor residential exposures measured in high-end buildings were 10 ppm. That's ppm with an M or greater. If you go to a nail salon, your concentrations exceed 15 ppm. When you look at the measured concentrations from Bella Romero at 2.1 ppb, we are multiple orders of magnitude below what would be typical exposures in either industrial or residential settings, or even outdoor air settings in an urban environment. So, to summarize our assessment, our conclusions were consistent with both CDPHE that had consulted with ATSDR that this was not a cause for concern. But there was significant public concern. And why was that? At best, there is a public perception that the only safe dose is no dose, and that the industrial operations cause fear and uncertainty. And this is not easy stuff for the community to follow. So for policymakers, there are common pitfalls in considering these health risk assessments. The first is assuming that a hazard is a risk. Identifying potential hazards is not the same as identifying risk. It's not just enough to know that something could cause a health effect at some concentration. You need to compare those exposures to concentrations where toxicity occurs. Second is the exposure assessment itself. You have to depend on proper data. You need to understand the duration and the intensity, and the data that you're collecting needs to be compared to the appropriate standard. Third is understanding dose response, and that the dose makes the poison. The route of exposure and the mechanism must be considered, and that the benchmarks that you're comparing to account for this conservatively and are developed by specialized experts. And then finally, you need to characterize the hazard. Put it into context with background or daily life exposures. Understanding that an exposure to a level above a benchmark MRL does not mean that adverse health impacts occur. It's a screening value. If you're below the MRL, there's no issue. If you're above the MRL, then you need to study closer for specific exposures and specific populations to actually assess whether there's a risk to public health. And finally, you need to consider the intent of the various health-based benchmark values when evaluating the exposure measures for risk. In short, the dose makes the poison, and that you cannot fall into the only safe dose is no dose. The whole process now is complicated by the proliferation of community science. Air quality sensors are being deployed widely, and I would note that these are not monitors, they are sensors. They're becoming widely available and they're inexpensive. This allows for the community to collect data, but it can be of dubious scientific quality if you're not careful. In many cases, the contaminant of concern is not measured directly, but employs surrogates like methane that create uncertainty or misinformation related to the actual exposures. Now, that's not to say that the community science and these sensors cannot be useful. They can be useful provided they remain within the confines of a rigorous, unbiased health risk assessment framework. You cannot have an agenda either way going into these studies. You need to consider all the available data, properly reduce that data in the context with the appropriate health guideline. And the bottom line is, you cannot cherry pick from the universe of available data based on a quasi-scientific study to raise an alarm to drive public policy. And that's a lot of what we see these days is when folks are seeing any detection on a sensor, not much less a monitor, there's concern because there is an exposure above zero, and zero is not the background. And before I close for questions, I just want to leave you with a quote I find compelling. This is from Sir Arthur Conan Doyle, the author of Sherlock Holmes and one of the founders of community science. It expresses that the proper approach to employing science in development of public policy. And that is that you have to find the facts first, unbiased and without agenda, and then let them inform your theories and policies. Otherwise, what you do is you twist the facts to suit your policies. And before I close, I would like to acknowledge my colleagues who contributed to this presentation. We have had a large team at Ramball who helped pull this information together. And I will take your questions if you have time.
Do we have any questions for Eric?
Great job, Eric.
Looks like somebody has their hand raised. Detlef, do you have a question?
Yes, I do. Can you hear me?
Yes, sir, yeah. I can hear you.
Okay, good. Well, thanks for the presentation. So, I actually have a few questions. One point here in particular is that you presented some results from using satellite data, looking at changes in methane by utilizing local or data from pixels that represent the front range versus over the background. And it looked like that resulted in projected emission decreases in methane of 52%, if my notes are correct.
Yes,
and
sir.
I wonder how you view these findings in respect to a recent NOAA peer-reviewed publication that was conducted by a group of NOAA scientists and university scientists using data from the Boulder Atmospheric Observatory, 10 years high accuracy data. They segregated the data based on transport directions, and then when they were segregating the data for transport from the oil and gas production region, they saw no notable changes, basically no notable changes in methane and also VOCs, particularly using oil and gas tracer VOCs. I think they used propane in that case, over a 10-year window. So it looks like, you know, that's very much in contrast to the findings that you're presenting here. And I was a little bit surprised that those findings from the NOAA study were not recognized or compared with the data that you have presented here.
So the READY study that we're showing here, which is this preliminary analysis, looks at both that Boulder data that you're talking about as background. But what we did in collaboration with CDPHE, with Gordon Pierce and his group, is look at what the appropriate background would pull. Now, this is satellite-based data that is looking at the entire air column, right? Pulling out the background from Mauna Loa. Now, the NOAA study you're referring to, is that the Pfister or the Gabby Hoffler study, or who's the primary author?
The lead author is Sam Oatmans from the NOAA Global Monitoring Division.
Okay. So,
and this is data based on 10 years of monitoring at the Boulder Atmospheric Observatory, which was located in Erie.
What's the publication date on that? Because this study that I'm referencing was we completed in February of last year.
This was published last year, 2021.
Okay. So it may be coterminous with it, and that's thank you for bringing it to attention, because we certainly would want to corroborate what that study is saying with ours. What this is simply stating, and what's not depicted on this graphic, is the ground level concentration measurements, and in particular, when you compare that to what is being observed with ethane at the Platteville monitor, is showing the trend. Now, if there's something in the NOAA study that is showing that there's a flat change, I think we need to make sure that we've got an apples to apples comparison, right, on what these data are telling us.
Yeah, I would strongly encourage you to take a closer look at the NOAA study, because I think the conclusions derived from that study are not quite consistent with what you're showing here. Also, we have a paper in preparation that looks at Boulder Reservoir data starting in 2017. And quite similarly, we do not see indications for declining methane emissions when we separate the data by flow direction. So I think there's a little bit of inconsistency here between these different data sets and analysis approaches.
Sure, and these data right now are currently being published for peer review with I think you're familiar with Patrick Reddy and Gabby Pfister. They are these data are currently going through journal publication. So certainly, I'm sure in the peer review process that those would be compared.
Okay, thank you.
Appreciate that question. I see Mr. Thomas has his hands up.
Yeah, thank you very much for the presentation. It's always good to just see different things added to things. I've been involved with ozone policy making in the Denver Metro for about 20 years. And so it's just interesting to see additional pieces over time. One thing I would say is that, you know, Bella Romero, right? I think people all understand that drilling and exploration of the pad is a temporary feature, right? Could be 6 months. Let's just say it's 6 months, right? And so, you know, with those concentrations at various intervals, when the camel was near the school, you had a lot of hourly readings above 1 ppb. And I can tell you from doing monitoring in downtown Denver that 1 ppb is, you rarely see 1 ppb from continuous VOCs, right? And so it's not that, yes, it's far below 9 for the ATSDR value, but it's not far below an integrated exposure limit for like Cal, right? And advocates know, they know all of these different, is it a short term? Is it a long term? But I wouldn't say that I would breathe easy knowing that you have a lot of values, hourly values over 1 ppb. That's worse than, you know, downtown Denver, which has a greater, you know, concentration of motor vehicles and the exhaust that comes from those. So it's tricky. I get what you're saying. I understand, you know, it's complicated to explain risk to the average, you know, the average person. But to just, you know, kind of, nobody really relies on the TSDR value. I mean, occupational, maybe near a refinery, sure. But even then, you're not going to see concentrations like 2 ppb. That's pretty rare to see that. So just, that's my 2 cents in terms of how you kind of talk about that in the future.
Okay, is that a question or a comment?
It's both comment, but probably more a comment.
Okay, yeah, I will say the slides here prepared for the Belo Romero Academy were prepared by an MIT educated PhD toxicologist, Dr. Deborah Caden, who wrote the report. And so I definitely will take her expert opinion in consideration. I think the point, though, that I wanted to make is being alarmist around single events or comparing to a zero dose, right? Because I think part of the issue, like you said, communicating risk to the public is very hard to do. And I can tell you from experience in a regulated industry in North Boulder County, you know, the public perception without being informed by policymakers and regulators properly is that the only safe dose is no dose. And the caution is that there are background levels there already, and you know, and we live in a risk benefit space, meaning that, you know, you're not going to be in a situation where any industrial activity is going to be zero dose or zero dose over baseline. And so I only caution that we properly contextualize the risk relative to baseline or to everyday exposures.
Yeah, no disagreement there.
Okay. It seems Dr. Helmick has his hand up again.
Yes, thank you. Yeah, I kind of like to second the previous comment. You know, we've been monitoring benzene now at 5 different locations here in the Front Range, continuously over up to 4 or 5 years, hourly. So we have, maybe 50,000 plus measurements of benzene right now at these different locations. And we don't have a single site and a single week of measurements where benzene levels were as high and as abundant as in these data that you're showing here right now. So what you're showing here is really unusual, and it's really high. And as I said, it exceeds every measurement that we have conducted. Just as we just heard a moment ago, we rarely see values over 1 ppb. The other thing I want to emphasize is that these were the measurements at that camel trailer that was sitting, you know, at a selected location at a fixed site, probably based on availability of space and power. You got to bear in mind that these are plumes that are transported to the trailer from a distant source, and you know, plumes dilute during the transport. So any point between the source and the trailer itself would have had higher levels than these data that you're showing here.
Yeah, but what
so I would let me finish, please. So I would be careful, you know, advertising these or presenting these as lower or maximum levels, because for sure, you know, there's citizens out there that are exposed to higher value when they are, you know, in closer proximity to where these emissions are released. Another point I want to make, from ours and many others groups analysis, we've learned that in the oil and gas plumes that we're seeing here in the Front Range, benzene is a very minor fraction. I think it's on the order of 0.2 or 0.3%. And the presentation here, the way you put it together, focused on benzene, and I think there's good and valid reasons to do that. But bear in mind that there is 500 times more VOCs, vapors in mass in this plume than benzene itself. So we're looking at this data right now here, that's 0.2% of the VOC mass that is in these plumes. So any citizen out there will be exposed to, with every breath to a VOC loading that's 100 times higher than what we see in these data points here. And we know very, very little about the health effects from exposure to these multiple VOCs in mixtures at a given time, and how individuals respond to this. So we're right now just picking one compound because that has been studied the most. We have the best knowledge on that, but I really don't know well, what the effect is of the 300 times, 500 times more other chemicals that citizens are subjected to at the same moment in time when we encounter these data that you're showing in this graph here. So I just want to throw this in as a few additional points of consideration in evaluating these data and in communicating potential health risks to the public.
Sure. And I'd like to counter with a couple of things. So first is the focus of the reason benzene is presented here is exactly that. It's most studied. It's also the one that was the contaminant of concern. And the report that Ramboll did on the Bella Romero Academy, if you've read the report, looks at all of the constituents that were measured. And they did measure a full suite of VOC. In the interest of time and space on the graph, benzene's where we focused. And benzene was the only one that actually showed a hit above an MRL. Second, I understand the concept of exposure to multiple VOCs. I will tell you, I've got 2 decades of experience quantifying emissions in this industry. And the other part to consider too is the emissions profile from the different phases is very different. Your sources of benzene emissions are going to be vastly different than, say, your sources of propane emissions. And then finally, you were talking, I think you were hinting at comorbidity of risk, looking at sort of the suite of compounds. And I will tell you, there's been very little done on looking at exposure to multiple compounds as opposed to isolated health risk. Again, I go back to the only caution I say here is it's not to say that there is no risk. There is never zero risk, but it's the avoidant or putting things in the right context to avoid alarmism, right? Because let's face it, there are lots of folks out there collecting information and collecting data and disclosing information for the purpose to drive a policy agenda or public policy agenda. And it's important to properly contextualize these without agenda in order to communicate the public health risk. But thank you for your comments, Doctor.
Do we have any other questions for Eric? All right. Well, I think this has been this was a very interesting presentation, and it's nice to have these conversations in a public setting like this. So I appreciate everybody's participation. Eric, thank you for presenting. And everybody, we'll see you soon, hopefully at our next meeting. Thank you.
Thank you. I appreciate the time.
Thanks, Brian.
Thank you.
Appreciate it. Thanks.